From the last video, we saw how to model an inductor and a capacitor in both the S domain, where we have these additional pseudo voltage sources that are reliant on the initial conditions. So from this, we can look at an example, and we're going to say that the initial condition is that there's 1 amp going through the inductor at time equals 0 from the left, or we can say that that's also equal to t, where time equals 0. So in the time domain, if we wrote a KVL around this circuit, what we would get is this equation here, where we have our complex voltage minus the voltage over the resistor minus the voltage over the inductor equal to 0. And we could set this up to solve this differential equation. It's not too complex, but it's doable. And we could find the current and then take the derivative of the current times the inductance, and that would give us our voltage. But because we're looking at using the shortcut of Laplace transforms to make the circuit analysis easier, let's try to see what advantages that might be able to do. So if we convert everything for our KVL, we simply get this 3 divided by s plus 8 term, this current now in the S domain, and then we just use our relation for the derivative for the inductor, and that gets set to equal to 0. And if we looked at how our circuit transforms as well, you can see that you get this initial condition term that makes this pseudo voltage source. So from the equation we set up, we can simply rearrange it to solve for the current, and we get this kind of annoying term here, which we can just simplify into this term. And what we want to do is enforce partial fraction expansion, such that we set the term we arrived at here equal to a divided by s plus 8 plus b divided by 2s plus 1. And partial fraction expansion isn't too complicated. Again, if I go into math courses, I'll get into that. But assuming the knowledge is already there, what we get is that a is equal to minus 1/5 and b is equal to 12 divided by 5. So then we can rewrite our current simply as this. And from here, there's 2 options we can do. We could find the current in the time domain, take the derivative of that, and arrive at the voltage. Or we could keep working in the S domain and just find out what that voltage is, and then convert that voltage back. Either way works. But something may appear a little bit striking here, and if we consider t before 0, this term blows up. And that's what we want to avoid, is having functions go to infinity. Now this is where you need to recall kind of the trick with Laplace transforms, where if we looked at a function f and Laplace transformed it, we would get this equation here. But this integral is also equal to this integral, where we had the unit step function just hanging out. And yes, you could swap the zeros for 0 from the left for the sake of what we're going to be doing. So because of this kind of quirk, we need to add a unit step function to this voltage when we transform it back, such that before t equals 0, this is equal to 0 and the voltage is equal to 0. Next, we can look at another example where we have a little bit more complex of a circuit, but we want to find both of the currents I1 and I2 in the time domain, and we're going to assume that all the initial conditions are equal to 0. So we can simply transform the circuit in the time domain to the S domain to arrive at this circuit here. And we can do a mesh analysis where we have mesh 1 and mesh 2 for the left hand and right hand sides. So if we set up those 2 mesh, we arrive at these equations, and using substitution, we can simply solve for I1 to arrive at this whole term, and then we can plug that back in to the second equation. And now we get a very, very long equation, and this looks just as time consuming, if not more, because you're probably going to have a pretty large partial fraction expansion. Might take a lot of time. But let's consider what this circuit is looking like in the time domain if we analyze it that way. So if we set up the meshes as we had before, we get M1 and M2, where now we have integrals and derivatives in the differential equation. We can try to clean them up just a little bit to arrive at these 2 equations on the right. What you can see from these equations is that from the top one, you have I1, and then you have I2 in there, and from the bottom one, you have I2, and then you have I1 in there. So you have a couple differential equations. And this is where it's really dependent on what the circuit looks like for the best analysis technique. So what's easier? The choice is yours, but from experience, what I've noticed is that the more complex and messier a circuit looks when you start to do KVLs or KCLs, the messier the math becomes. So do you either want messy math in a differential equation or in an algebraic equation? I'd probably take the algebraic equation, less likely to make critical errors. And if we look at what the current for I1 was, we actually go through and carry everything out. This is the entire term in the time domain. So you can see you have 1, 2, 3, 4 terms here. You have exponentials, you have cosines, you have sines, and those are coupled with exponentials as well. So that looks pretty terrible to deal with in the time domain. So I'd suggest Laplace transforming circuits is pretty useful.